So there are a couple of things I want us to look at associated with this derivation. We started by looking at particles bumping around in a box, and we were trying to connect the microscopic, that is momentum, kinetic energy here, with macroscopic, that is temperature. So we've gotten to average kinetic energy, so a microscopic, something that's information on a small scale, connected to a large scale measurement. Now, you may or may not remember that this 3 actually came from, if we look at this, we have 1/2 mv, this average kinetic energy is average v squared is equal to 3/2 kBt. And while we were doing this, I don't know if you remember, but we said v squared is equal to vx squared plus vy squared plus vz squared, and we argued that these were all, each of these words, about the same if we're talking about averages, right? The average speed in the x direction is about the same as the average in the y and average in the z. And so we had said v squared is equal to 3, say, vx, average vx squared, or 3vy. And if I plug this in here, what you can see is that 1/2 m 3vx squared, average speed in the x direction, is equal to 3/2 kBt, or that you have 1/2 mx vx squared is equal to 1/2 kBt. And so one way to think about this is the kinetic energy associated with the motion in the x direction contributes 1/2 kBt to the internal energy, right? This internal energy, which is a 3/2 times the number of particles. And then being able to move in the y direction contributes 1/2, and being able to move in the z direction contributes 1/2. That's in fact where we got this 3. It came out of here. And so what we say is we can generalize this to say for every degree of freedom, is what it's called, degree of freedom, and we'll talk about what that means in a minute, we get an additional 1/2 kB added to our internal energy. So for a monatomic particle, we can move in 3 dimensions, right? So 3D motion. So we have something like E internal is equal to 3 times 1/2 kBt times the number of particles. If we have 2 particles, a diatomic molecule, that's we can think of as a rigid rod, then the whole thing as a rod has 3D motion, right? The whole rod can go up, down, left, right, but there's also internal energy. So this degree of freedom is really a count of internal independent, internal is kind of redundant because we're talking about internal. So really independent ways of contributing to the energy. So if we think about this, having 3D motion and being rigid, then there's also kinetic energy, right, for rotation. There's rotation about the long axis, and then you could imagine rotation about this, right? So kinetic energy of rotation, we've got 2 different moments of inertia. There's one where it's a long barbell and we're spinning it like this versus spinning it around its edge. Obviously, when we're spinning it around like this, this would be a bigger moment of inertia because the masses are further away than if we spin just along an axis here, okay? So I've got 2 more degrees, so I have plus 2, so this gives us an internal energy of 5 times 1/2 kBt times N. Now, that doesn't even include, if we increase the temperature, it turns out not only can we move from this rigid, we can then take this two diatomic molecule. So this is monatomic here. Monatomic, so we're talking noble gases here. This is diatomic not too hot, and then we add more energy, a higher temperature, and we're getting to some quantum mechanics now, then we can also have vibrational energy. So then we can have vibrational motion. We can think of it as a little spring. So this becomes a spring that can bounce back and forth, and we get both kinetic energy of the relative motion to each other, but we also have potential energy of the spring. And so we get 2 more, and so this can go to 7 times 1/2 kBT in. So that would be for diatomic. So we have more thermal energy. So this isn't quite constant with temperature, right? At some point we sort of make this jump, and it is fairly quantized here. Finally, if we're at 3 or more particles, so I get 1, 2, and 3, sort of, I don't know how we're connecting them exactly. We'll do a physicist version of these here. It's not a very good model. We could do it like that. It's probably more likely we have something like a triangle, right? That seems more likely. The bonding looks like that, and we can have spring models in between these, something like this. And then we can get 1 more rotational axis out of it. And so for polyatomic, we can get our internal energy to equal 6 times 1/2, or 3 kBT in, or it can go to 8 with the vibrational. We get to this when we add, this is when we include vibrational energy, okay, at high enough temperatures. And so the issue here is that when we talk about the internal energy, we're most often going to use this expression. But this has a little bit of an asterisk for us. This is for monatomic, right? If we've got something besides a monatomic atom, right, besides an atom, then we need to know a little more information. We either need to know that it's in the range where we just have rotational contributions. If it's diatomic, that it goes up to 5, or polyatomic, it goes up to 6, or something else. So that extra information will need to be there. But in general, we use this, we're just saying it's a monatomic ideal gas. So that's the first implication that shows up with this. I should also say that while I have this asterisk here, having this 3 saying that the energy contribution to the internal energy, that we get 1/2 kT for each degree of freedom, in this case for monatomic that would be for X, Y, and Z, is called the equipartition of energy. And all that means is that the energy is equally shared between all the degrees of freedom. So that's the argument I made, that something is just as likely to have kinetic energy in the X, the Y, and the Z direction. There is no preferential direction for that. Okay, the next thing I want to do is focus on this. These are some implications of what we've gotten here. This was our average speed squared. And what we did is we could say we could get a sense of the average speed by taking the square root of that, and we called that our RMS, sort of an average speed. It's the square root of the average of the square. So that would be this square root of 2 kBT over m. So it's a way at getting at what is the average speed. But what the speed is at a particular temperature, there's really a speed distribution, right? So if we have gas in a room, which we do, air in a room, then the speed is sort of, this is one of the averages that we can talk about, but the speed can be pretty widely distributed around that average. And so if we're interested in sort of the probability, just so you can get a sense of what this looks like, the probability, how likely it is to have a particular speed, we have something called a probability distribution. And this is our speed, Okay, so not our velocity, this is our speed. So it can be in any direction, right? This is just the magnitude, what the speedometer is saying. And so at one temperature, this kind of looks like this. So this would be at T1. At higher temperatures, it's going to be shifted over because the speed, the average speed gets higher, but it also flattens out. So at higher temperatures, it kind of goes like this, okay? And this VRMS is not actually the peak, it's a little bit off from the peak. So for this one, this is my VRMS, say for this, and then it's like over here for this one. And what this probability distribution does, it says, well, at VRMS, we're fairly likely to have this speed versus a speed that's, I don't know, twice as high, if this is really to scale, twice as high, or half the this speed, okay? But it's still possible. And so what we recognize is that the way we find this, the way we sort of read this is we can say the probability of a speed in some range, of a range of speeds, I guess I want to say, of a range of speeds. Say, what's the likelihood of having a speed between here and here, right, would be the area under the curve, is the area. Or mathematically, that would be an integral, right? The integral under here tells us how likely it is. Maybe this is 20% of the total area. So that the total area, is the way these probabilities work, the total area of this blue curve needs to be 1, and the total area of this more orangey curve also has to be 1. Under this curve has to be 1, right? All of that has to be 1. But if we want to find the probability of getting a particular speed, we can just read it sort of off of here. That would be its probability. Or we could find the area to say, suppose we're plus or minus 5% of this value. And of course, this is my peak, my peak speed, my most probable speed. And if I've got this distribution, which I do, that equation, the equation for this blue curve, probability, it's written f of v, for example. F of v is equal to some constant for a given v times v squared e to the minus mv squared over 2kbt, where this a is given by 4 over square root of pi times m over 2kbt all to the 3 halves. Now, I'm not going to expect you to know this or do much with it. The point is this a you pick up by just saying that the area under this curve has to be 1. So mathematically, you take the integral of this from 0 to basically infinity, v being infinity dv. So we'll tell you that what a has to be equal to. So you do that integral and everything works out. And that's how you get this value. The point of this is that, oh, and the peak, right, you would get by just taking the derivative of this, and you can get the equation for this peak speed. The point is that this gives you this kind of, it's not quite a Gaussian shape, but it's almost a Gaussian. Well, it's not almost a Gaussian. It's going to be basically a probability of distribution. And as you get higher in temperatures, this bigger T, it turns out that if this is a smaller number, that spreads this out. And so that's how that comes about. You can graph this out to see what it looks like.